Yeah, so hi everyone. I'll be talking about my work, improved early warning of compact binary mergers using higher modes of gravitational radiation. So just to introduce, gravitational waves are nothing but freely propagating perturbations in the fabric of space-time caused by accelerating masses. As you can see in the cartoon on the right-hand side, two black holes merging each other, and the gravitational signal is radiating away from them. This is a new window of astronomy to study the universe, which was invisible through electromagnetic observations. The strongest known sources for these kind of signals are binary black hole, binary neutron star, and neutron star black hole mergers, etc. So till now, we have observed of the order of like 100 compact binary coalescence events, including the EM counterpart from one of the two BNS mergers detected. In the next 2 years, we expect that of the order of 1,000 CVC detections will be made. So not only the gravitational signal from such compact binary mergers, we can also observe EM emission, which happens mostly after the merger. And while the GW signal is stronger in the pre-merger or during merger region, that can be used as an early warning to notify the EM astronomers to look for any EM emission. So one of such EM emission we observed with the multi-messenger follow-up of a GW signal from a BNS merger, which was detected on 17 August 2017, which actually enabled an unprecedented science gain. For example, to mention a few, for example, it pointed that BNS mergers are the central engine for short gamma ray bursts. It also pointed a new class of optical transients, for example, which are called kilonovae, and also hinted towards the heavy elements formation sites. Heavy elements, I mean here, like platinum and gold, and also led to the measurement of expansion rate of the universe, and many more. But in this case, the pre-merger early warning or the early warning GW detection and localization alert got delayed by 30 minutes. That might have led us to miss any EM emission or information before the merger. So ideally, we expect that pre-merger alert could lead to detection of EM emission prior to the merger, and also any possible information about an intermediate merger product, and also can shed light on the complex physics of merger and post-merger phases of the binary. So what is the status of current early warning? So current early warning efforts are targeted to BNS-like mergers, which are near symmetric in masses and also not too heavy. And these BNS mergers are always almost expected to produce EM counterparts. A technical term we use called EM bright. So on the right-hand side, in the cartoon, I put the signal duration for various compact binary mergers detected by LIGO Virgo in the first and second observing run. In the bottom, you see the signal, 3 seconds of the signal duration of the first BNS merger, although it lasted for about 3 minutes in the band. So what you see that BNS mergers are relatively lighter, hence they will spend more time in the frequency band of the detector, hence providing more window for the early warning, GW early warning. So what about the heavier binary mergers, like for example, NSBH, neutron star black hole mergers? So the first question will be to ask whether it is worth pursuing early warning for such systems. So, NSBH systems could be EM bright if the tidal disruption of the neutron star happens outside the innermost stable circular orbit called ISCO. It actually depends on two properties. One is the equation of state of neutron star, how easily you can tidally disrupt the neutron star matter. And the second is the spin of the black hole. So large spin reduces the ISCO radius, increasing the chances of tidal disruption at a relatively smaller binary separations. Now, since NSBH systems are heavier than BNSs, it will lead to a smaller end-band duration, providing relatively small window for early warning as compared to BNSs. So the question to ask is it possible to increase time gain in this window? So answer is yes, we can use the higher modes of gravitational radiation. So just to give you a background, like how the signal emitted looks like, from a compact binary merger, we can write the signal as a multiple expansion where different multipoles are functions of intrinsic parameters of the binary. Intrinsic parameters, I meant here the component masses and the component distance. And the angular dependence of the source is captured by the spherical harmonics here. Basically, the orientation of the plane of the binary and the initial phase. And this signal scales as inversely with the luminosity distance. So as you can see, the first term in this expansion is the L equal to 2 and M equal to 2, which is the dominant mode, and it's called the quadrupole mode. The higher modes, which corresponds to L greater than 2, are important for sources with high asymmetries. For example, high mass ratio. Mass ratio is defined as the mass ratio of the component binaries, basically M1 divided by M2. And recently, the existence of higher modes has been confirmed through observations. So how higher modes can help us to improve the early warning efforts? So for non-processing binaries, you can write the oscillation frequency of any multipole as a multiples of orbital frequency of the binary, and that will lead you the time to coalescence for that binary as you can see in the bold here. So FLM divided by M to the power minus 8/3, and that will lead to the in-band duration of any higher mode HLM, which will be a factor of M by 2 to the power 8/3 larger than the corresponding dominant mode. You can also see this in the cartoon here that the 4/4 mode will have a longer in-band duration than the 3/3, and 3/3 in turn larger than the 2/2. So you will have more window for the early warning. Just to demonstrate how the early warning is going to help us, so we choose one system, one NSPA system, where the primary mass of the black hole mass is of the 15 solar mass, and neutron star we choose as 1.5 solar mass. And we set the inclination of the plane of the binary as 60 degree and locate this as a 40 megaparsec. And we choose the optimal sky location that minimizes the sky area. And we choose the O5 sensitivities of the LIGO Virgo Kagra detectors. This is a network of 5 detectors with sensitivities projected to 5th observing run of LIGO Virgo collaboration. So in the plot, we show the sky area and the SNR evolution as a function of time to coalescence when we include higher modes and we do not. So what you see here, the sky area and the sky area are consistently smaller at a given early morning time, and the SNRs larger when we include higher modes as compared to when we only look at the analysis done using dominant mode. So this clearly tells us that the higher modes, including higher modes, will be quite important for us to localize the system early in the time. So we do a population study. We simulate 55,000 NSPH injections, and we distribute the masses of neutron star between 1 to 3 solar mass, and black hole from 5 to 60 solar mass, and we distribute them uniformly in sky locations and orientations. And we choose 3 limiting distances. We distribute up to 40 megaparsec, 100, and then 200. And this plot actually basically shows the cumulative histograms of all these localization sky areas for these systems for 3 different early warning times: 20 seconds, 40 seconds, and 60 seconds. And what you see, if you focus on the rightmost panel, if you focus on the topmost corner here, so this corresponds to O5 observing run. And what you see that for an early warning time of 60 seconds before the merger, you see that inclusion of higher modes will lead to sky area improvement by a factor of greater than equal to 2 for approximately 60% of the systems. And this number can be improved to 70% or increased to 70% for these NSPA systems in Voyager scenario, which is a second generation detector scenario with sensitivities improved by a factor of 2 to 3. So not all NSPA systems will have EM counterparts. So we try to see how much of them, how many of the systems will be EM right. So what we basically do, we choose equation of states for neutron stars, and we consider only one limiting distance scenario. We distribute them up to 100 megaparsec, and we choose two spin distributions. So EM right, as I mentioned earlier, it depends on two properties. One is the equation of state, and another is the spin of the black hole. So we choose various.
10 minutes.
Okay, thank you. So we choose various range of equation of states, and that you can see here the if you choose one isotropic spin distribution of the black hole, the band corresponds to here different equation of states. And what you see here, that the aligned spin distribution will lead to higher fraction of EM right binaries as compared to isotropic one, which is just to be clear, because higher spin magnitude will lead to higher chances of tidal disruption of the matter. So if you focus again on the right-hand side plot, the rightmost panel, for the O5 scenario, what you see that the improvements for the aligned spin distribution or aligned spin distribution is better by 20% for 20% as compared to the isotopic ones. When you consider a reduction factor, a sky reduction factor greater than or equal to 2 with the inclusion of higher modes. And this width of this band here, this represents the variation in the equation of states, and that is only mildly like 10%. So not only the localization of the event, but you can also look at the number of galaxies in a particular localization volume. So what you can do, you can combine the localization accuracy with the distance estimates, and then you can predict how many number of galaxies can be in a localization volume that can host the merger. So this plot here corresponds to the number of galaxies localized for different early warning times. So for example, if you see the vertical panels correspond to observing scenarios, the first one 45 seconds before the merger, then second 45 seconds. And there is another observing scenario, this is called 3G. This is a third generation detectors with sensitivities improved by an order of magnitude. And here we are looking at around 5 minutes before the merger. And the color map here represents the number of galaxies here, and the x-axis correspond to mass of the black hole, and y-axis correspond to mass of the neutron star. And these are dotted and solid black contours here represents the equation of state that demarcate the region of EM right NSPA systems. So what you see here, that the improvement, if you include higher modes, the improvement factor can be of the order of 1 to 2.5405. If you look at 45 seconds before the merger, and this can increase to 4 in Voyager scenario for the same early warning time. And if you look at the third generation detectors, even if you look at 5 minutes earlier, you will be able to reduce the number of galaxies by a factor of 10. For systems, all these systems are located at 100 megaparsec here. Okay, so just to summarize this work, including higher modes can improve the ability of pre-merger detection localization of NSPS mergers. This can have potential high payoffs in the understanding the complex physics of binary mergers. So one side note that higher modes may provide significant improvements, but these may not always result in tighter sky areas or significantly less number of galaxies localized. So of the sky areas of the order of 100 square degree may be covered by a joint effort involving multiple telescopes, especially if assisted by a galaxy catalog. Also, the improved measurement of distance and orientation can help astronomers to better determine their follow-up studies, whether the source will be detectable in EM or not. So that is all. Thank you.
Hello. Yeah. So first, it's kind of slightly tangential question, like how regarding this statement that you can the recent observations, you can confirm that there are higher modes. How do you do that? Like how do you say that there are higher modes?
Yeah. So basically, you have theoretically predicted model here. So if you restrict your theoretical model up to dominant mode, and if you do the mesh filtering and you subtract the power from the observed data, you will have some residual power. And if that power is consistent with the, like, let's say the next dominant mode is 3-3 mode, then you can say that the higher modes detection is confirmed there.
Okay.
So that is how we do it.
Okay. Thank you.
Slide. You said something. Can you just go to the last slide?
This one?
The last slide, basically. Yeah. So HMs may provide significant improvements, but these may not always result in tight sky areas. Is this because of biases, or what is this because? I mean,
Yeah.
What does this mean?
Yeah, so if you look at for a given early warning time, you're looking at the ratios, right? So ratios might be quite, let's say if I talk the ratio is by a factor of 3, but the individual sky areas can be of the order of 1000 degrees square, right? So ratio, although ratio is quite attractive, but these always may not result individually.
You're making an absolute statement here instead of a relative statement.
Right.
Okay, got it. Thank you.
Okay. Thanks, Mukesh.